Hi, I guess it's almost time and we're going to start with the time for everyone. 5 o'clock now. So I'm Roger, I work for Citrix on what's called a platform team internally. It's a group of people inside of Citrix that we work only on open source projects. In my case, that's mainly Zen, BSD, and we also do, well, I also do some VM and other things from time to time, but Zen and FreeBSD are my main aims there. And I'm here today to present the work that we've been doing during the last year, which is trying to make the mode that we use for DOM0 much more similar to what we call HVM. I will go in a little bit more of details if you're not really familiar with that, about what DOM0 means or what HVM means and so on. So I structured the presentation into a first part of the Zen introduction, for those of you that don't know Zen. Then I've also got a second part that describes the limitations of the current interface that we use for DOM0 and Zen. And then I've got the last section is how we are going to improve that interface in order to overcome the limitations that we have right now. And finally, I've also got a small section about how that's going to affect FreeBSD. So yeah, for those of you that are not very familiar with Zen, this is a typical diagram of a Zen system. On the bottom we have the hardware with all its devices, the CPU, the platform devices like the NMIU, part of the CPU actually, but the PID, the HPED, all those kind of platform devices, plus the PC devices and so on. Then on top of that we have Zen, which is a microkernel that runs directly on top of the hardware and basically takes control over the CPU and a couple of platform devices. It mainly needs a timer in order to do scheduling, and it also needs the MMIU in order to manage memory. It also takes over the virtualization extensions, either Intel or AMD, in order to create guests with those extensions. And then when Zen has finished initialization, it creates the first domain. That's a special domain. It's called the control domain, or DOM0, because it's the first guest that's created on the system, and this guest has a lot of privileges over Zen, basically, because it's capable of creating new guests. It basically has control over the system, and then this guest gets all the PC devices passed through to it. So basically Zen doesn't contain any kind of drivers for PC devices or anything like that. It doesn't know anything about the storage or network or anything like that. All the drivers are inside of the control domain. That's very important for us because it prevents us from adding drivers into Zen itself. So we reuse the drivers already present in the control domain, and then we can avoid adding a lot of code inside of Zen. And then on top of the control domain, I put a lot of, some processes that you can have running on DOM0, like Xterm or syslog or Xorg or DHCP client or SSHD, whatever you want to put there. And then on the side, I've also added 2 guests. You can, of course, have as many guests as you want. And as you can see in this slide, the control domain and the guest from a Zen point of view are on the same layer. There's really not a lot of difference between the control domain and the other guest. It's just the privileges that they have over Zen. And then this kind of guest can either be a PV, which is a paravirtualized guest. It's the first guest that was supported by Zen, and it has a very specific interface, a very intrusive interface. Or they can be an HVM guest, which is much more similar to what everyone is used now in virtualization, which is basically an emulated PC guest that has access to all the platform devices, and it contains the devices that you would expect from a PC. And here I have a slide of a type 2 hypervisor. I would like to show the difference on how they work or the design in general. Here we have the hardware, and then we have the operating system on top that contains hypervisor code inside. And then on top of that we have what will be run by a type 2 hypervisor, like the processes and the guest. And in this case, for example, one of the main differences I think between type 2 and type 1 is that on a type 2, your processes that you have on your host compete for resources with the other processes that you have running. The guest, all of them compete for CPU, they compete for memory, it's all shared, and they basically use the same scheduler also. So now I would like to speak about the current interface that we have for DOM0. That's very similar, well, that's basically the PV interface, because DOM0 has always been a PV guest until now. So basically we are a lot of interfaces that are different from a normal PC environment. There are 4 of them that I think are the most relevant, that are different from a normal PC. For example, PV.0 doesn't have access to the MMIU, doesn't have access to CPU enumeration techniques that are present on all the hardware. The delivery of interrupts is also different, like the setup and the delivery of interrupts is completely different from bare metal. And finally, there are also some differences in the ACPI tables and the information that they contain. So the MMIU is the memory management unit. It's present on the CPU package and it allows you to create mappings between virtual space and physical address space. And on Zen, that's very different because you don't really have access to this piece of hardware. So instead of using the normal way of managing the MMIU, you have to issue hypercodes into Zen. And then Zen will configure the MMIU for you. This, although it seems not very problematic, it actually is because there are no architectures that have different implementations of the IUMMIU or different interfaces for the IUMMIU. So what Zen did was introduce a different MMIU interface on x86, and that's very problematic because it requires you to modify the core of your OS, the memory management code, and that's something that's not very nice in general to do to OSes. Because then you will have to either have a separate kernel like NetBSD does. NetBSD has a kernel to run on Zen that contains the PVM implementation, or you have to add hooks like Linux. Linux added a bunch of hooks to the MMIU code in order to have both the native and the paravirtualized MMIU code at the same time. And really I don't like any of those solutions and I don't think they are necessary now. Also, one of the problems of the PVI MMIU is that it's limited to 4 KB pages only. You cannot use huge pages or anything like that. It's only limited to 4K. And as said, it involves using hypercodes in order to set up all the page tables. There's also another kind of issue that's when you run as a TP guest, you cannot issue privilege instructions. You have to issue an hypercode and Zen will execute the privilege instruction for you. Privilege instruction here will be loading the GDT or the IDT or all of these privilege instructions. You cannot really do them inside the guest. So you actually need more code there in order to be able to do that when running on Zen. Here I have a slide that shows the difference between how we handle CPUs on Zen and on bare metal. On Zen PV guest, of course. For example, the Boottime enumeration of CPUs on native is usually done nowadays using the MADT ACPI table. That's something that's found on all modern computers. It's an ACPI table that contains the list of CPUs present on the system. And that's what's used by the OS in order to detect CPUs at Boottime. On Zen, of course, this is different, and we don't use that table. Instead, we use hypercodes. This means that we have to modify very early OS code in order to do the CPU enumeration using hypercodes instead of ACPI, which is again not very nice. The bring up of secondary CPUs is also done using the local APIC or the X2 APIC on bare metal, but on Zen we also need to use hypercodes because we didn't provide the local APIC to PVGuest basically. So we also need to use hypercodes in order to do that. And then finally the hot block of CPUs on native is done also using the ACPI tables and what's called the general purpose event block that signals the OS that there's a new CPU. This again on Zen is completely different and we do that using Zen store. I mean the list here it's not very big also, the list of differences, but those differences are very intrusive because it means that you need to modify the early boot code in order to do the CPU detection using a different technique. And the CPU bring up is also completely different, which is not very nice in general. Then regarding interrupts, that's something that we changed a lot for PVGuest. So basically on normal bare metal x86 systems, you have two different kinds of interrupts from physical devices. One of them is the legacy PCI interrupts that are routed over the IO APIC. There's a line directly connected to the IO APIC and this will inject interrupts into your local APIC. And there's a newer kind of interrupts that was introduced later that's called MSI and MSIX. These are O2 fans interrupts that are basically injected directly from devices into the local APIC by writing to specific memory addresses that's trapped by the local APIC. And this is the way to set up the interrupts on x86 basically. And then the configuration, well, this is the way the hardware delivers interrupts on each 86, and the way to configure them is done using the PC configuration space. So you have, well, for the IO APIC, they are directly routed into specific port, into specific pin of the device, and for the MSI and the MSIX, you choose which vector on the local APIC you want to use, and that's set using the PC configuration space. So on Zen, as I said before, we don't have a local APIC, so basically the way we deliver interrupts inside of the guest is completely different. We use something that we call event channels. That's a virtualization technique of interrupts, and we route physical interrupts over these event channels. And basically the event channel is not more than a bitmap on memory that Zen will modify in order to notify the guest of an pending interrupt, and then it will also send a proper notification in order to make the guest aware that there's been an interrupt delivered on that map. And also the configuration of interrupts is performed using hypercodes, which means that we need to modify the MSI and the MSIX code and the legacy PC code in order to use hypercodes in order to configure interrupts from physical devices. This can be more or less hidden behind the generic interrupt code on FreeBSD. So you don't need to modify each device in order to use something different in order to set up interrupts, but again, it's something that's not very nice to have because it's the core part of the OS and we are actually modifying it. So here I have a slide that shows a typical injection from an interrupt from hardware into the hardware domain. The interrupt goes to the hardware local APIC that's controlled by Zen. Zen receives the interrupt and then injects the interrupt into the guest using the event channel device, and the guest processes the interrupt. And finally, the last point where we differ quite a lot from bare metal is on ACPI tables. That's the method used by hardware in order to deliver the information about the environment where you're running. Basically, you fetch all this information from ACPI, or almost all of it. And there are two different kinds of tables on ACPI. One are the static tables. These are tables that are very easy to parse because they are completely static in memory. You can map them to a CS structure, and it's not really hard to parse them. And then there's another set of tables that's much more harder to parse, that's called dynamic tables. And these are written using ACPI machine language, AML, which is a specific language that you use in order to create, well, in order to deliver those tables, and then you need an AML parser inside of your OS in order to extract the information from those tables. And, well, it's done that way basically because you can also have methods inside of AML, so you can have like kind of code inside of AML that the OS will execute. So it's slightly complicated and it requires quite a lot of code in order to parse all this information on the OS. And so far on PV.0, what we have done is basically pass the tables as they are from the hardware to DOM0. So basically DOM0 gets the tables from native. This seems nice, but the main problem here is that DOM0 can have a different configuration from the one that described from the tables. For example, you can configure DOM0 to only have access to 2 CPUs, but maybe the system has 10 CPUs. What happens then? If DOM0 parses these native tables, it will find 10 CPUs and it will think it has 10 CPUs, and that's all. So this is one of the main problems that we have here, well, especially with the static tables, was this, that the number of CPUs is different on the tables from bare metal, and then we are providing those tables to Zen, and that one. There were also the problem that there are some devices that will probably hide from DOM0 on those tables, and we don't want DOM0 to access them because they are used by Zen, so we basically want to hide them. Like one of those devices, for example, will be the IO MMIU. It has its own table that's called VMIR. That's a table that describes the IO MMIU hardware, and this is owned by Zen, so we don't really want DOM0 to know anything about this device, so we need to hide it. One of the problems that we have here is that Zen so far can only pass information on the static tables. It doesn't have an AML parcel because that's considered too big to be inside of Zen, because Zen is a microkernel and its code base is quite limited. So we basically can only gather information from static tables inside of Zen. But there's certain information inside of the dynamic tables that we need for Zen. This is a list of what we need basically, which is the hot block of physical CPUs. This is inside of the dynamic tables, and we need Zen to be aware of this. The CPU states, that's also something that's inside of the dynamic tables, and finally the sleeper state, that's also part of the DSDT, that's the main dynamic table. And all this information needs to be known by Zen, because Zen is the one that will set the CPU states on the bare metal CPUs, because Zero cannot really do that. It doesn't have access, it doesn't know the load of the whole system. So it needs to be Zen the one that sets these states. And basically, so far, we have to provide this information from DOM0 into Zen, so that Zen knows all this information and can properly react on them. And another option that we have considered, and we are maybe still considering, is to import an AML parser into Zen. I know that the OpenBSD guys have an AML parser that's not very big, it's maybe 4,000 lines of code, and I think it should be able to decode all this information. And really, we don't need a very clever AML parser, because we only want to look at the tables, but we don't want to execute any methods from the tables or anything like that, because there can only be one entity that uses the methods on the tables, and that needs to be DOM0. It cannot be Zen. So basically, while we are still considering it, and we are still trying to see how much it will simplify the architecture to include a simple AML parser into Zen in order to fetch all this basic information, so that we don't need DOM0 to send this information into Zen. So seeing all these problems that we have with the current interface, or all these limitations that we have at the moment, we decided that we wanted to do something slightly different, and that we wanted to do something as close as possible to bare metal, so that we don't need to modify the OSes that want to run as DOM0 as much as possible. I mean, it's quite likely that we will need to do some modification, but we want to limit that to the minimum possible. Another important point of doing that, of being close to bare metal or to the native interface, is that then we can take much more advantage of the hardware virtualization extensions present on modern CPUs. That's something that both Intel and AMD is doing. They are coming up with newer extensions to allow you to get more performance out of virtualization. So we really want to make use of that, and in order to make use of that, we need to be as close as possible to bare metal. And as I said, we only want to resort to using hypercores when we have no other way of doing specific tasks, so we would like to avoid it as much as possible. So first, in order to get rid of the PV IOMMIU, that's something very easy, because now using the hardware virtualization extensions present on both Intel and AMD, you can create what's called a second stage page table for the guest. So basically, the guest gets virtual MMIU, and it gets, it's completely transparent from a guest point of view, which is like the physical memory that we want it to see. And that's something that we really want to do. Another advantage of using that hardware virtualized MMIU is that then you can make use of all the page sizes available on the architecture. So we will be able to make use of 2 megabyte and 1 gigabyte pages without any kind of modification to the guest or Zen or nothing. And basically all this allows us to use the native MMIU code present inside of OSes, so we don't need to add any more hooks or modifications to the memory management code inside of OSes. Then the interrupt management is something that we have been doing very differently on Zen, and now we would like to get as close as possible to bare metal. So in order to do that, one of the first things that we need to do is to provide a local APIC. This local APIC is going to be either emulated by Zen, or if you have a newer Intel or one of the new AMD boxes that is coming up to the market very soon, the hardware itself is capable of virtualizing certain parts of the local APIC, so you don't need a lot of emulation code. And apart from a local APIC, we'll be providing an emulated IO APIC to the guest, so that you can basically use legacy PCI interrupts without using hypercores or anything like that, and they will be delivered to the emulated IO APIC. And finally, the configuration of MSI and MSIX interrupts is also going to be performed using the PC configuration space. That means that we will need to grab accesses to the PC configuration space from inside Zen, and we need to detect when the guest is trying to configure an interrupt, and we need to react properly. So basically, we'll have a set of traps inside of Zen that will detect those accesses to MSI and MSIX regions, and we will probably set up the emulated interrupts for Zen, for the guest. And then you don't have to use hypercodes anymore in order to set up interrupts from physical devices. So this is what it's going to look like, what we plan to do, or what we are actually doing. You have the device at the bottom, then the device injects the interrupt into the physical AP, and then Zen receives this interrupt and it injects the interrupt into the emulated APIC of the guest. Or if you have what's called posted interrupt, that's a kind of new feature of Intel. The interrupt can be delivered directly from the hardware device into the emulated local AP. That's something that certainly helps to reduce latency of interrupt, because you basically don't have to go inside of Zen, so everything is much more faster. Then regarding ACPI tables, we have decided that what we will do in DOM0 case is that we are going to modify the well, not really modify, we are going to provide another set of ACPI tables to DOM0. So what we basically do is we are going to craft some tables for DOM0. That's mainly the MADT table. We are going to create this one specifically for DOM0, so it contains what DOM0 has access to. If DOM0 has access to 3 CPUs, we will create an MADT table with only 3 CPUs, and we will pass that into Zen. That allows us to get rid of all the hypercodes in order to detect CPUs at boot time. And then there's something in the ACPI spec that tells you that if you provide CPUs, local APIC entries on the MADT, you also need to provide processor objects. So what we are going to do is that we are going to add an extra table also to the ACPI in order to contain the processor objects that match to the MADT objects that we provide to DOM0. And finally, for those devices that DOM0 is not supposed to have access, or those devices that are taken over by Zen and that DOM0 cannot manage, we are going to use a table that's called STAO. It's the status override table in ACPI that allows you to hide devices. Basically, you can put the ACPI namespace inside of this table, and DOM0 should avoid poking at that specific device. So, what does it mean to FreeBSD, all these modifications that we are doing to Zen? First of all, it's going to introduce a little bit of disruption to FreeBSD Zen DOM0, because we are going to switch from the mode that we are using now to a different mode. So now we are using PBH3.1, and that's something that unfortunately we are going to remove because it's not really working properly. And we are going to switch to what's called PBH3.2. That's what I'm talking about here. This is the PBH3.2 architecture. And that means that there's going to be a little bit of disruption while I change the code on FreeBSD in order to support these modes. I expect that's not going to be much, or even it's not going to be noticeable. But well, there's always a change. Then, as I said, the PBH3.1 code is being removed from Zen. And what I will do on FreeBSD is I will probably commit the PBH3.2 code, and then soon after probably I will remove the V1 code, so that we don't really have a space of time where we are not able to run as DOM0. But yeah, we'll also need to test it. So there's a change that something that worked before are not going to work now, but we really need to do that change, because PBH3.1 is going to be removed from Zen altogether. There's also something that I like a lot. That we are going to be able to remove quite a lot of Zen-specific code in FreeBSD, so I will have less code to maintain on FreeBSD, and that's something that makes me very happy. So basically there's a folder inside of x86/Zen. There's a lot of the PB code, like the code to manage the interrupts from physical devices, all this code. the code to do the early CPU enumeration using hypercalls, all those kind of things. I'm basically going to remove them. So it means less code that I have to maintain. Another nice thing about PVHV2 is that we will be able to run on AMD hardware. PVHV1 was limited to Intel hardware due to the way it was designed. So now when we do the jump to PVHV2, we'll automatically be able to run on AMD hardware without requiring any further modifications. And well, as I said, I have less code to maintain and the interface is much more closer to bare metal. So I think that's an improvement overall. Yes, so the conclusions of this talk will be that we are trying to make Zen as close as possible to bare metal, the interface, especially the interface that we provide to DOM0. That's why the talk is named towards an HVM DOM0. It's not going to be exactly like bare metal, but it's going to be very, very close to bare metal, which means that we will need to modify a lot less FreeBSD or Linux or any other OSes that we want to port into Zen. This also allows us to take advantage of a lot of hardware virtualization extensions, the one that we have now and the one that are probably going to come up in the future. They are going to allow us to get rid of some of the emulations that we do in software, and instead of using software, the hardware itself is going to provide that emulation for us. It will also allow us to reduce the maintainership burden that we have of Zen code inside of OSes. Since we are reducing the code, we are getting much more close to bare metal. It's going to mean that we'll have less work to maintain all this code in all the OSes that we want to support. And this brings me to my last point, which is that since the interface is now much more closer, much more simplified, much more similar to bare metal, we expect that we are going to gain support for other operating systems, because it's going to be much more easy to port Euro OS to run as a PVHV2 guest and as a PVHV2 DOM0, because it's going to be basically very, very similar to bare metal. Yes, so that's everything I had about PVH DOM0 V2. If you have any questions, I will take them gladly. Yeah?
Can you know which version of Zen PVHV1 will be removed?
In the next one? Yeah. On FreeBSD, I will keep the port maintained for PVHV1 until we can make the jump to PVHV2. But the next version of Zen will already have this code removed, because there's already quite a lot of PVHV2 code inside of Zen. It's just not yet ready to provide the same functionality as PVHV1. But I expect that, well, the next release is going to be 4.9, and this release is not going to have PVHV1 support, neither PVHV2 support finalized. And the next one, which is going to be 4.10 or 5, I don't really know which kind of numbers we keep. The next one is going to have the full thing, so it's just going to be one version that we're going to skip basically on FreeBSD.
Does it work on HVM DOM-U as well? Is this support suitable for only DOM0?
No. This is basically already done for DOM-U. It's already inside of Zen, so now we have PVHV2 guest that's already done, and we already provide the local APIC and ACPI tables to that guest. So we basically, you don't need the hypercalls in order to do CPU enumeration, and you can do CPU bring up using the local APIC. The only thing that we are missing on a DOM-U side or on a guest side is pass-through. Pass-through of physical devices is not yet finished, but it's going to be exactly the same way, so we are going to provide an emulated PCI host bridge to DOM-Us. Yeah?
Do you think Zen server will move to FreeBSD?
To be honest, no, I don't think so. Not at least for the moment. I don't know in the future. Right now, I think they are going to stick to Linux because, well, I'm the only engineer on Citrix that does FreeBSD, so I would really prefer them to stick to Linux, or else I will have a pile like that of bugs that I need to deal on my own. So yeah. Yeah.
How do I check different from HVM mode kernel and domain mode kernel?
How do you check it?
Check different from like
From inside the guest, or
guest OS. Guest OS model.
yes, from inside of the guest itself.
Domain or HVM.
Yeah. The easiest way we have to do that for FreeBSD, you mean, or for Linux, or FreeBSD?
As possible, both.
Oh. Well, on FreeBSD, you need to look at the boot messages, and you will see something like booting on PVA. And the same for Linux, I think. You need to look at the DMS, and you will see something like
Oh my god.
using PVH extensions. I think it's on Linux or something like that.
There's no sysadel or something like that?
No, because I don't think it's really useful to know. I mean, well, it's not really that you care that much. I mean, you're running there, so yeah. I mean, it's something that's important for the administrator. So you set on the config file whether you want to use PVH or HVM. But if you get given a guest there, I mean, there's nothing that you can do in order to change that mode. There's nothing specific that you can do while you are on PVH or on HVM. So, yeah. I guess I could add a CCTL. That's interesting, but you are, well, it's just curiosity, I would say. Last questions? Thank you very much for your attention.